Okay, I'm going to finish up what I want to tell you about the atomic theory of gases this morning. And if you remember the last time I introduced this idea of mean free path, the average distance that a molecule in a gas can go before it whacks into another molecule. And we talked about how this is the explanation for why the molecules in a gas are traveling at these amazingly fast speeds, and yet it takes an appreciable amount of time for a smell, say, in the back of the room to reach us up in the front of the room or something. It's because these molecules are slowed down so much by bumping into all the other molecules. And we actually use that idea of mean free path to figure out what the size of the molecules has to be. And well, let me just see if anybody has a good memory for numbers here. Does anybody remember the distance that a molecule goes before it bangs into another molecule? Nick?
500 nanometers?
Yeah, 500 nanometers, right. So that's just about the, if you remember when we studied light, that's just about the wavelength of green light, for instance. Now, it's a really short distance, obviously. It's about a, somewhere on the order of a millionth of a foot, right? Or something. So it's a small distance. Now, what's the size of a molecule that came out of knowing that? Neat. Yeah, about a third of a nanometer for the size of a water molecule. So, that's a billionth of a foot. So we're getting really small numbers here. But the physicists found that they could use this idea of the mean free path to understand not only how molecules, spread out in a gas, particle diffusion is what they called that, but they could also understand heat conduction. For instance, if you had a cold room and a hot room, and there was a door between them, and you opened up the door, okay, it would take a while for the temperature in the two rooms to come to the same temperature, for the cold room to heat up and the hot room to cool down. Well, the time that it takes to do that, physicists could actually, like Maxwell, could actually work out using this atomic model of the collisions between the molecules and how long it takes for, hot molecules to bang into the other cold molecules and transfer their kinetic energy to them. And sure enough, it turns out to be exactly what they found in experiment. So they could explain not only the particle diffusion, but also the heat conduction of gases using this exact same model and this same idea of mean free path between molecules, between collisions. So, but there was one other thing that came out of this theory that Maxwell thought was very, very strange. And that's what I want to tell you about this morning. I think I started to tell you about it at the end of last class. This idea that Maxwell decided to look at at air resistance. For instance, if you have a pendulum and you start it swinging, so let me see, what do I want to call this? Say Maxwell's analysis of effect of air density on pendulum motion, call it that. Obviously, this won't really just apply to pendulums. This will apply to anything moving through the air. But what Maxwell decides to try and compute is how does the effect of the the amount of air, the density of air, the pressure, affect the damping of the pendulum. I mean, if you swing a pendulum back and forth, it won't just continue to swing back and forth with the same amplitude. The amplitude will slowly decrease due to the air resistance. So what happens if you, say, put the pendulum in a container and you start pumping the air out? Okay, now I think I gave you the surprising answer at the end of last class, right? So that you can pump half the air out, say, and it doesn't affect the damping of the pendulum at all. The pendulum still, say if you have a pendulum where you started out swinging at 30 degrees back and forth, and then you time, how long does it take to get down to half that amplitude, to go down to 15-degree swings? And let's say at normal air pressure, it takes 2 minutes. Okay? Now, then you pump out half the air. You do the same thing again. Well, you would think, now, since half the air is gone, there's got to be less air resistance. It should take like 4 minutes to go down to half the amplitude, if it took 2 before. Well, what Maxwell showed is that, at least he showed it mathematically at first. He didn't go out and do experiments. He just did the analysis using this simple, superball model of gases that we've been talking about. And he showed that it doesn't work that way, that there's a peculiar effect. And you can, let me just, okay, here's our pendulum. Now, you have all these air molecules around. They're actually not arranged in rows like this, but it's easier for me to draw them that way. And I will have a point about that. Now, you have all these air molecules and the pendulum swinging through them. Now, what Maxwell realized when he started doing this analysis was that, according to the atomic theory, the pendulum bob it's not like sending the pendulum bob through a liquid. Okay, if you had a pendulum bob that you were, swinging through, say, water, okay, it would have to push all that water out of the way in order to get through, right? And if you imagine swinging it through water versus swinging it through some really heavy liquid like mercury, well, obviously, it's going to go through the water better than it's going to go through the mercury. The mercury is going to slow it down a lot quicker. But Maxwell, when he did the gas theory analysis, realized that there was something fundamentally different about what was going on when the pendulum bob goes through a gas, because it doesn't have to push all this air out of the way. Because when he started actually working out the details of this analysis, he realized that these molecules out here that are away from the pendulum don't matter because there's no chance. The only way they could slow down the pendulum is if, say, this molecule out here could actually come in and whack against the pendulum, right? But let's say that this distance here is what I've been calling L, the mean free path. Well, some molecule that's 3 or 4 mean free paths away, even if it's heading toward the pendulum, what's going to happen to it before it gets there?
It's going to hit another molecule.
It's going to hit another molecule and be scattered off in some other direction. It's never going to hit the pendulum, even if it happens to be heading in the right direction. So it's almost see, what Maxwell realized then was these molecules have 2 functions, really. Yes, some molecules are hitting the pendulum and slowing it down. But these molecules close to the pendulum, the ones that are actually able to, if they're heading in the right direction, hit the pendulum and slow it down, they also serve another function. They're keeping the other molecules from hitting the pendulum. They're in effect shields. They're between the pendulum and the other air molecules. So, I mean, it's just, you can think of it this way. It's like you go to a concert, okay, and there's this crowd, and everybody wants to get up on stage with the performer, okay, but the only people that really have a chance of getting up on stage are the people in the front row, right? The people back have all the other people in their way. They can push forward all they want, and they're not going to get there. Okay, so even if you have a huge crowd, you only need the same. I mean, it's the same number of people. The people in the however many people you have in the front row that actually have a chance of getting up on stage. So those are the only people you have to guard against, in effect, if you're security at the concert. The same sort of thing is going on here. It's only the molecules that are within like one mean free path, that are causing the damping of the pendulum. And so what happens now if I double the number of molecules here? Okay. That's right.
Even though, there's still a shield, so it really doesn't make a difference.
Yeah, I mean, what happens when you double the number of molecules is you also double the molecules maybe really close to the pendulum, but in effect, you make this mean free path half as much. And there's still the same number of molecules within one mean free path. And if you do the opposite, if you take out most of the molecules, well, now the mean free path has gotten bigger. Okay. But Maxwell found that there's still the same number of molecules within one mean free path. So there's still the same number of molecules that actually have a chance of hitting the pendulum and slowing it down. Over a wide range of densities. Now, obviously, if you take out all the molecules, the air resistance has to go to 0. But over a wide range of air densities, this model of this idea that the air molecules are serving these two functions. They're, yes, the ones close to the pendulum are causing it to slow down, but they're also shielding the pendulum from all the other molecules. That idea actually works over a wide range of densities. In fact, you can actually decrease the density of the air by a factor of 10. Pump out 90% of the air. And it has almost no effect on the damping of the pendulum. But Maxwell hadn't done the experiment yet. He had just done the mathematical analysis, and he got out this weird result. Okay, it seems to be counter common sense, right? So his first thought was, well, this is actually going to be evidence against this simple atomic model of gases here. That I found something wrong with this theory. Because this can't really be true, and yet it's an implication of the theory. So there must be something wrong with the theory. But he thought, well, we should at least go out and make sure that this isn't true. Test it experimentally. Now, in fact, Maxwell if Maxwell had been a little bit more knowledgeable about the history of physics, far before his time, he might have realized that there had been previous physicists who had noticed this exact effect experimentally and commented on it and thought that it was strange and thought maybe there was something wrong with their experiment. But, for instance, the first guy who found experimental evidence that you could take out half the air and not have any effect on the pendulum was a contemporary of Newton back in the 17th century, Boyle, Robert Boyle. He's I've mentioned him before. He's the first guy who discovered the first primitive form of the gas law, that at a constant temperature, the pressure times the volume of a gas is equal to a constant. Okay, that was Robert Boyle, and he was the first guy. I mean, the vacuum pump had just been invented right before he started doing his work. And he was the first to really do a lot of extensive experiments with vacuum pumps. And one of the things he thought of doing was swinging a pendulum in a chamber where he had pumped out some of the air to see how the air density affected the damping of the pendulum. And in his notes, in his book, he just has this passage that, yeah, we thought of doing this experiment, and we tried to do it, but we didn't find the effect we were looking for. That there didn't seem to be any effect on the damping when we pumped out most of the air. And he just notes this like it's an experimental failure on his part. That oddly enough, we didn't see what we expected to see, and then he just goes on to describing other experiments. But Maxwell, 200 years later, figures out, well, this is why, Boyle didn't see what he expected to see. Now, and there was actually another physicist who had found this effect in the 1820s, and again, it just struck them as strange. But here, now that they have a theory to explain it, now Maxwell is really motivated to find out whether this is really true, and he wants to do some accurate experiments. So he goes out, he does those experiments much more accurately than Boyle was able to do them, and finds out that the theory is exactly right. And this is particularly impressive when this happens in science, where you see a strange result, completely unexpected result, emerge from a theory, and then you go out and do the experiments, and lo and behold, it turns out to be true. So this, I think, for those of you who are still doubting that matter is made of atoms, this should, you should be getting to the point where you're putting those doubts aside now. This is another impressive piece of evidence. Okay, so let's sum up what we've got now on our list of evidence for atoms. There is a little bit more chemistry I want to tell you about. We're going to go back to chemistry this afternoon. And how many of you know something about what's called the periodic table? Oh, wow, you've all seen that before. Okay. Well, that's what I want to talk to you about. We're going to start talking about that this afternoon, because that is the next, that's the development in chemistry that happened in the 1860s, this same time period where Maxwell is doing his work on the atomic theory of gases. I think it was during this time period that you could actually call the atomic theory proven in the 1860s. And let me just back that statement up by summarizing the evidence that we've looked at now, and then we can think about how, does this constitute a proof? How strong a case is this? Okay, so on our list of evidence for atoms, the law of multiple proportions, all of this should be pretty familiar to you now. And this was Dalton, 03. Good. You can remember this one actually because, well, we're in 2004 now, so it's not exactly 200 years, but it's almost exactly 200 years since Dalton first put forward the first strong evidence for the atomic theory of matter. Okay, now, law of combining volumes. Now, empirically, this was discovered by French chemist Gay-Lussac, 1808. And again, just briefly remind you about these laws. What Dalton discovered was that in chemical reactions, the elements combine in definite ratios of their masses. And when two elements combine in more than one way, there are these integer ratios of the masses, which made him think in terms of atoms. And what Gay-Lussac found was the same thing for volumes. That, you have these, when volumes of gases combine to form some other gas, they combine in these integer ratios of their volumes. And because things in these chemical reactions are always combining in certain integer definite ratios, it obviously it makes a very strong case for thinking in terms of atoms, which have to combine in integer ratios, obviously. Okay, now, allotropes and what's the next word I'm going to write? Dan? Isomers. Again, this is just another very strong piece of evidence, I think, for atoms. It's the fact that you can have the same stuff, but it exists in two totally different forms. The only way you can explain that is with a theory that where matter doesn't just depend on the stuff, it depends on the arrangement. And that's the atomic theory has that property, so it can explain things like allotropes and isomers, whereas some just continuum theory of matter can't explain these things. Okay, so let me see, actually I'm not putting names and dates here because there's several different chemists who discovered these allotropes and isomers, but it started in I guess the first was Humphrey Davy in 1814, where he proved that graphite and diamond were the same stuff, right? And then there was a bunch of them in the 1820s. Okay, so the law of electrolysis, which is Faraday, 1832. Now, Faraday again basically showed that when you use electricity to generate a chemical reaction, okay, the amount of electricity is directly related to the number of atoms that react chemically, that react in your chemical reaction. So it's like each atom generates a certain amount of electricity. There's this constant relationship between the amount of electricity and the number of atoms. And unless you're thinking in terms of atoms, you can't explain that relationship. So again, the atomic theory offered an explanation, whereas the scientists who didn't think in terms of atoms, were drawing a blank on why this law would be true. Okay, now all of this, notice, this is evidence from chemistry. Now we also have now seen a whole bunch of evidence from physics. What's the first law, Troy?
The law of heat capacity.
Yeah, law of heat capacities. Give me names in a year.
Dulong, Petit, and
Okay, 1819. Right. Dulong, Petit, 1819. Okay, and again, this is relating the amount of heat that a material will absorb to the number of atoms that it has. So again, explaining the variations in heat capacities of different materials just by reference to the differences in the number of atoms that those materials have. Oh, here's one too. Let me see. Call it relationship between heat and motion. And that is, first, who did it? Evan. Joule. Any idea on the year? Okay, 1845. So what are you doing in your history class right now? What period are you in?
We're just about to start James the Sixth in England around the 1600s.
Oh, okay. So I'm a little ahead of you. All right. Yeah, it's a lot easier to remember these dates, of course, if you can just associate other things that are going on in history at the same time. But, if you know a little bit about U.S. history, for instance, we've been talking about this gas theory that Maxwell developed in the 1860s. What else was going on in the 1860s? Civil War. Okay, so Maxwell was actually doing all of his most important work, or most of his really important work, right at the time of the Civil War.
Was he in Europe?
No, he was in England, but
So it didn't really matter to him.
yeah, it didn't matter to him. But it's just a good way of relating. Making sure that these numbers aren't just numbers to you, that they mean something. If you can think about other things that are going on, at the same time. Okay. What comes next here? Troy?
Waterston's.
Yeah, right. The law of gases. That's a big one. And that is right at the same time as, it's just after Joule did his work on the conversion of heat and motion. Now, Joule's work was important to the atomic theory because it's really an implication of the atomic theory. And according to the atomic theory, the whole idea of explaining heat is, heat is just the motion, the internal motion of the atoms. So if, on the atomic theory, a certain amount of motion has to create a certain amount of heat. And so there had to be this constant relationship between motion and heat if heat really is just motion, according to the atomic theory. And Joule proved that there was. Now, Waterston actually uses this simple model of gases, this superball model that we've been talking about, to explain the gas law, that had been known, the relationship between pressure, volume, and temperature that had been known since the 1780s. And then finally, let me just say, let's see, atomic theory of gases explains diffusion, heat conduction, and damping due to air resistance. So this same simple model of gases that Waterston used to explain the basic gas law, Maxwell and a few other physicists use to explain why molecules diffuse through the air at the rate that they do, why heat is conducted through gases at the rate that it is, and why the damping of objects due to air resistance doesn't depend on air density. Yeah, Sam. Oh, damping due to air resistance. Okay, so now all of this, these last 4 items, so we got a total of 8 here, and the first 4 were from chemistry. The last 4 are from physics. And now we have, now I think this is an impressive list at this point. And this, like I say, let me see, Maxwell's final paper on his major paper here was in 1867. Okay, so by the 1860s now, you have to be really stubborn in order to deny the existence of atoms, because you've got just this enormous range of evidence coming in from chemistry, just based on the way that chemicals react with other chemicals. And then you have this enormous range of evidence in physics, most of it having to do with heat, but also a whole theory of gases that not only explains the relationship between the pressure and the volume and the temperature, but explains how gases move through other gases and how heat is conducted in gases and why air density doesn't matter much in resistance. At this point, you think, well, all the scientists must have believed in atoms, right? Turns out that actually they didn't. Now, the explanation of why scientists didn't all believe in atoms at this point it's a long story that I've actually, I think you listened to a lecture that I gave on this, but it has to do with confusions about basic scientific method and what can be concluded on the basis of this kind of evidence. I mean, some scientists were still, the basic confusion was they thought that they had to be able to see atoms, basically, in order to really believe in them. And you can see here, I mean, after we've gone through all these items, that you can make a really strong case for the existence of atoms, even though no one's ever seen one. You know, so you can think of it like a scientist is a detective. And the detective doesn't have to have seen the murder, before he can conclude who did it, right? I mean, he can have all kinds of circumstantial evidence that add up to an absolutely foolproof case that Joe killed Bill, okay? Even though he didn't see Joe kill Bill. And maybe nobody saw Joe kill Bill. And the same thing goes on in science. And it took a while for scientists to really grasp that point. Some of them were still bothered by the fact that they couldn't see atoms, but you can see this is a hard case to argue with at this point. Okay. Let me see. We've got a couple of minutes left. Like I say, I'm going to add one more item to that list, and the next item is going to be from chemistry, and then we're going to call this case closed. And we know that atoms exist, and it's just a question of now, what is their structure? What is an atom exactly? And that's what I'm going to tell you about next. But before I do that, let me. We've covered a lot of material from different areas now, and I want to do a little something to try and tie it together. So. Let's look at 4 areas that we have studied. Motion, electricity, heat, and chemistry. And think about the relationships between these 4. And I think, let me see. Let me make this a little more symmetrical. Okay, now we know there's a relationship between motion and heat, right? That if you rub 2 sticks together, they heat up, right? So you can turn motion into heat. Can you go the other way? Can you turn heat into motion? Yeah, what would be a good example of that?
Steam.
Yeah, exactly, a steam turbine. I mean, exactly what goes on in any power plant. That's what they do. You take heat, you produce expanding steam to turn a turbine, right? So, yeah, there's a strong relationship between heat and motion. I mean, a direct relationship, and it goes both ways. You can use motion to cause heat, and heat to cause motion. What about the horizontal dimension here? Chemistry and electricity. Is there any direct connection there? Yeah, try.
You can use electrolysis.
Okay, in electrolysis. No, you're onto something there. What are you doing in electrolysis?
It's electricity to chemistry.
Exactly. Yeah, you're using electricity to drive a chemical reaction in electrolysis. So that would be what Troy said would be the arrow that goes from electricity to chemistry. What about the other way, Daniel? Absolutely, a battery. You're just taking a chemical reaction and generating electricity with it. So that definitely goes both ways. Now, so we'll continue filling in this diagram and thinking about it this afternoon. And then I'll get into the last issue of chemistry that I want to talk about.